Project 4.1 TI-84 Code Repository. This project consists of a repository of about 17 different programs that were used during UBC's first-year engineering mechanics course. The primary objective of this project was to make the TI-84 calculator compatible with vector operations, which it usually isn't. Eventually, the need for vector-compatible programs grew to algorithmic step programs that simplified the process of solving complex situations. The programs grew to include descriptive solutions of very complex problems and variable interdependencies within them, and lastly, to include multiple different solution generators for the same kind of situation. Programs are generally meant to solve equations using pre-saved formulas or algorithmic steps. It's very easy to write these sort of programs. This one, it's a program that solves for momentum using the coefficient of restitution, either solving for unknown final velocities in one dimension or the coefficient of restitution itself. And it consists of very simple instructions, a display instruction for text or variables somewhere down here. Display restitution, display E, that's a variable. And then also simple instructions like pause the program, it'll stop like partway through and say enter to continue. It'll switch the calculator's mode from radian to degree if it isn't already done. And then it'll also do prompt statements to fill variables on the spot. And then it can also do conditional statements with these variables to figure out like if it's solving for this or that, and if one thing satisfies another for a variable interdependency, how to save a variable or how to generate a solution with a given variable. All of the complicated instructions here, like for example, in this air resistance program, there's calculus instructions like fn int, and this you can get from the math print instructions that are labeled all in this left-hand menu, including some special characters like this arrow, which is a store key, store 9.812G if you're using metric units, or 32.2 if you're using imperial units, for example. And then there's also other things in here like clearing all lists. There is a need to clear lists if you are using matrices, as shown down here. You can perform operations with matrices to store the new ones like this, reduce row, and then all these if-else statements are for program interdependencies again. I'm not going to explain the physics behind it. Some of these programs give you the option to use a variable at the very end if you're not doing anything else to solve with it. So this value, matrix F over here, can be used following the end of the program in short-term memory as your answer value. I'm going to demonstrate the capabilities of this, some of these programs. So for some of the dynamics programs in the mechanics course that I did, it'll require a dependency on a function. We have a function here. We'll open the program polar fn. Again, I'm not going to explain the physics here. I'm just going to show you how this program works. So we reach an instruction screen. Program requires y1, r of theta for path, calculator set to radian mode, enter to continue. So I press enter, calculates the forces and normal to path, f normal to arm, enter to continue. This is a physics concept from that course. The mass, we'll say the mass is 0.5. For enter theta dot as angular velocity and theta double dot as angular acceleration. So theta is pi. In this problem, theta dot is 4 and then theta double dot is 3. The next thing it's going to show us is the acceleration values for r and theta axes and the directions that they will point. So there, AR is that magnitude, draw AR inwards. A theta is this magnitude, draw A theta away from the direction of motion. And the next thing it's going to do is going to calculate the forces in this situation, and it's going to tell me which way to draw those forces to. So N should come out to be 4.5807. It's approximately that. You round, and it's a rounding error. N points roughly towards A sub R, enter to continue, and then F is going to be approximately 0.898. And yes, it is that. Enter to continue. F points away from A theta, and the program is finished. Thank you for listening.